All right, so we continue building our enterprise network. So right now, all three sites are fully reachable via static routes. So today we're going to replace all the static routes with OSPF. So the routers will discover each other's network automatically. So the IP addressing scheme is unchanged. So because today our routers, they stop being dumb boxes that only knows what we manually tell them, and they start talking to each other. So they start sharing information. So they start learning the network on their own. So today we configure OSPF, but before we touch a single command, I want just to make absolutely sure that you understand why OSPF exists, because if you know the problem it solves, then OSPF will just make a perfect sense. So think about previously, we had 14 static routes spread across 3 routers, right? Every time we needed to add a new subnet, let's say Cape Town, there's a new branch office in Cape Town, so we've got to manually update routes on every router. Okay, so 3 routers, 14 commands. So that's basically was for a small 3-site network. So imagine a company with 50 branches across South Africa. Let's say Johannesburg, Cape Town, Durban, Pretoria, Bloemfontein, East London, Port Elizabeth, Polokwane. So you will need hundreds of static routes, right? And when one link fails, say OpenServe fiber between Johannesburg and Cape Town just gets cut by cable thieves at 3 a.m. Nothing reroutes automatically, so the Cape Town office just goes offline. So it just stays offline until the engineer manually logs in and update the routing table. Now OSPF solves all of these: one configuration per router, automatic neighbor discovery, automatic route learning, automatic failover when a link goes down, and when a new subnet is added anywhere in the network. So every router just learns about it within seconds. So there's no manual update. OSPF just means, or rather stands for Open Shortest Path First, right? It's a link state routing protocol. Let me just break that down into 3 key concepts that just explains everything about how OSPF works. So a link state protocol like OSPF shares information about the state of each link. So it is up, or is it down? What is the speed? What networks are connected to it? So every router shares this information with every other router in the area. Now each router then builds a complete map of the entire network called the LSDB, link state database, right? And what it does, it independently calculates the best path to every destination using the shortest path first algorithm invented by, I don't know who invented it anyway. So, but then compares this to the distance vector protocol like the RIP, which only tells neighbors I can reach network X and Y hops, right? So without sharing any details about how to actually get there. Now, OSPF routers know the complete topology. So RIP routers only know rumors from neighbors. OSPF converges faster. It scales better, and then it makes a smarter routing decision. So OSPF is like having a complete, let's say, roadmap in your head. Let's say Bloemfontein roadmap in your head. So you know every route, every road, every traffic light, every detour. So when one road is closed, meaning it's a link failure, you immediately recalculate using your complete map, which is now distance vector is like asking directions from strangers. So each person only knows the next step, and wrong information actually spreads slowly. So the question is, will you trust Waze, which is OSPF, or random strangers, RIP to navigate the city during load shedding. So of course it's OSPF every time. Now OSPF uses areas to organize routers and limit how much route information will needs to be shared. Every OSPF deployment must have an area 0 called a backbone area. All other areas must connect to area 0. So now today what we're going to do, we're doing a single area OSPF. So all 3 routers in area 0. So this is the foundation. I think in future maybe we will just add multiple areas to for larger, more scalable designs. But for our 3-site network, single area is actually perfect. Now what is the process? So how does OSPF routers discover each other? Step 1, it's hello packets. So when OSPF is enabled on the interface, the router immediately starts sending the hello packets every 10 seconds, like the hello interval to the multicast address of 224.0.0.5. Any OSPF router on the same link receive this hello. And then step 2, it's a neighbor relationship. So 2 routers become OSPF neighbors when they exchange hello packets and agree on the same error ID and then the same hello or dead intervals, the same subnet, and if configured, the same authentication as well. And then step 3 is the adjacent information. Neighbors that fully synchronize, like LSDB link state database, become adjacent. So only adjacent routers will fully synchronize their LSDB, and then they share also full routing information on point-to-point links, like maybe our serial WAN. All neighbors become fully adjacent. And step 4 is the LSA flooding. Each router creates an LSA or link state advertisements describing its own links and neighbors. So LSA is just flooded through the area, and then every router receives every other router's LSA. And then step 5 is the SPF calculations. So with a complete LSDB, each router independently runs the SPF algorithm just to calculate the shortest path, or rather to every destination. So the results are just installed in the routing table as the O routes. So OSPF cost metric is based on the interface bandwidth. So there's no hop count like RIP. The formula is cost is reference bandwidth divided by interface bandwidth, and then the default reference bandwidth is 100 megabits. So a fast Ethernet of 100 megabits link has a cost of 1, and then serial link a 1.544 megabits T1 has a cost of 64. So OSPF always prefers the path with the lowest total cost. Now on the multi networks like the Ethernet, OSPF elects a designated router and a backup designated router to just reduce the number of adjacencies. Instead of every router forming an adjacency with every other router, which grows exponentially, all routers form adjacencies only with the designated router and the BDR. So the designated router just collects and distributes LSAs on behalf of the segment. So on a point-to-point links like there is our serial link, links between Johannesburg, Cape Town, and Durban, there are only 2 routers. So the DR or BDR election does not happen on point-to-point links. Both routers form a direct full adjacency immediately. Now, before we continue with OSPF, I need to explain the router ID because it affects the neighbor relationship, the DR and BDR elections and troubleshooting. So every OSPF router must have a unique router ID. So that is a 32-bit number that is written in a decimal format like an IP address. Now Cisco routers, they choose the router ID in this order. First, if you manually configure a router ID with a router ID command, that wins. And then secondly, if there is maybe a loopback interface, so the highest loopback IP becomes the router ID. Number three, if maybe there is no loopback, then the highest active physical interface becomes IP becomes the router ID. So the best practice is always manually configure the router ID. Do not leave it to chance, and because a predictable router ID just makes troubleshooting infinitely easier. So we'll configure our meaningful router IDs for each of our routers. Johannesburg is gonna be 1.1.1.1, and then Cape Town is gonna be 2.2.2.2, and then Durban is gonna be 3.3.3.3.3, so that it's easy to identify. All right, now we need, in our topology, before we configure OSPF, we need to remove the static routes that we added in the previous lesson. So if we leave both static routes and OSPF running simultaneously, then the static routes at AD1 will always override OSPF routes at AD110. So the routers will never use OSPF. All right, so let's go to Cape Town, start with Johannesburg, and then enable, and then configure terminal. Then we're gonna remove, we just remove no IP route 10.10.4.0 255.255.255.255.0. Okay, I've got like a lot of 255 now. .0, and then so we remove the static routes to Cape Town and Durban, and then we're just gonna keep the default route to ISP. So this 10.10.100.2. All right, so I'm gonna get it up again, and then I'm gonna remove so I remove Cape Town, I'm gonna remove Durban. Durban will be 101.2. Let's just make sure. And then here .4.0, and then here is gonna be 200. So 200, remember, is our ISP, so it's 200.1, which is our ISP. All right, we're gonna do the same thing. I'm just gonna wait for you, but we're gonna do the same thing to Cape Town as well, and then do the same thing to Durban. Okay, enable, and then configure terminal. All right, no IP route 10.10.1.0 255.255.255.0, and then 10.10.100.1, and then no IP route 10.10.2. remember now 10.1, it's our VLANs. .2 is the second VLAN, and then .3 is the VLAN, so we need to remove them as well. So notice the only thing I change here is I just change the VLANs, so because they're using the same router, so we don't change anything else. And then I'm gonna just change this 1.3. So again, they're using the same router, all our 3 VLANs. And then we've got Durban, Cape Town to Durban. which is 10.10.5. Right. So remember, from Cape Town to Durban we go via Johannesburg, so we're still using the same router here. Okay, and then we will remove no IP route for 10. Okay, let me just do this. So that we don't make mistakes. So here is going to be 10.10.101.0, which is our serial link, and then 255.255.255.252. So remember the serial link, and then 10.10.100.1. And then finally no IP route 0.0.0.0 slash 0.0.0.0, and then 10.10.100.1, and then end. Okay, so we'll need to do the same thing to Durban, and then enable, and then configure terminal, and so no IP route 10.10.1.0 255.255.255.0 10.10.101.1, and then do the same thing 10.10.2.0, and then 10.10.3.0. So we remove the VLANs, and then I think we must also 10.10.4, which is Cape Town. Remember, we go from Durban to Cape Town, we go via Johannesburg to Cape Town. So we must also remove that one. All right, and then no IP routes 10.10.100.0 255.255.252, which is 10.10.101.1. All right, and then the last one, no IP route 0.0.0.0 0.0.0.0, and then 10.10.101.1, and then end. Okay, now we need to actually verify static routes that are gone. So I'm just gonna go to Johannesburg, it's Johannesburg. Then we will just show IP route. So 200 is just, our thingamajig. So you'll see there is only C and L entries, which are directly connected networks. So there is no S entries. So all remote networks are gone from routing tables. So the pings are not gonna work. So the only static route that we've got is the one that goes to the ISP. You see that? So the pings between the sites will fail now, but only for a moment, because OSPF is about to bring everything back automatically. All right, while we're here, now the exciting part is that we're going to configure OSPF process 1 on all interfaces. Here, so we already enabled, so we're just gonna, I'm still in Johannesburg by the way, so we're just gonna configure terminal. Just to go to the configuration mode, configure a terminal. All right, so we're in the config mode. Then we're gonna do router OSPF PF1. So we're starting the OSPF process 1. All right, then we must give it the router. I said the router ID is gonna be 1.1.1.1. So we say router ID, it's 1.1.1.1. And then we need to advertise all networks on the Johannesburg router into OSPF area 0. So for example, we've got Johannesburg Finance VLAN, so we can say network 10.10.1.0 and then 0.0.0.255 and then area 0. And then we're gonna do the same thing with HR. So I'm just gonna press up arrow. So it is 10.10.2.0. Then we do the same thing with IT. Which is 10.10.3.0. And then we need to do the WAN link to Cape Town. So the WAN link to Cape Town is going to be different. Okay, let me just remove everything here so that we don't make mistake. So for Cape Town, it's going to be 10.10.100.0 and then 0.0.0.3 and then area 0. So area 0. And then for Durban, it's gonna be 101. Yeah, that's about the only thing that we changed there. And then okay, let me explain every part of this configuration carefully. So router OSPF 1, this starts the OSPF process. Now the number 1 is the process ID, right? It is locally significant only, so it does not need to match on any other routers. So think of it like a job reference number, right? So it is just how this router identifies this particular OSPF instance. So you can run multiple OSPF processes on one router, but for our main purposes, process 1 is all that we need. Then router ID 1.1.1, we manually setting the router ID to 1.1.1.1 for our Johannesburg router. It's simple, memorable, and then it's unique as well. Because Cape Town will get 2.2.2.2 and then Durban will get 3.3.3, and then the network 10.10.1.0 and then 0.0.0.0.255 area 0. This is the OSPF network statement. It has 3 parts: the network address, which is 10.10.1.0, and then the wildcard mask of 0.0.0.255 and the area 0. Now the wildcard mask is an inverse of a subnet mask. So where a subnet mask has the ones, the wildcard has the zeros. So in vice versa. So a 0 bit in the wildcard means this bit must match exactly. So a 1 bit means I don't care about this bit. Right? So subnet mask of 255.255.255.0 is what in binary? Is 81s.81s.81s.8 zeros in binary, right? So the wildcard mask is 0.0.0.255, which is 8 zeros dot 8 zeros dot 8 zeros dot 8 ones in binary. So the network 10.10.1.0 with a wildcard means that match any interface whose IP starts with a 10.10.1 dot something, right? And then enable OSPF on that interface for a /30 subnet like 10.10.100 .0/30. So the wildcard is 0.0.0.3. All right. So the last two bits they don't need to match, covering exactly for addresses, which is .0 to .3. All right. Now let's go to Cape Town and then configure OSPF. Configure terminal. So this router OSPF 1, and then a router ID 2.2.2.2, and then for Cape Town LAN, so it's network 10.10.4.0, and then 0.0.0.255 area 0, and then the WAN link to Durban, to Johannesburg. So it's network 10.10.100.0 0.0.0.3, and then area 0. Oh yeah, I see that. Look at the log message there. So after entering the OSPF config on Cape Town, and then look at the console, within seconds you actually see the log message of OSP5 ADGCHG process 1. You see that, and then NBR 1.1.1 on serial 0/3/0 loading to full. This means that the Cape Town router formed a full OSPF adjacent with router Johannesburg. You see that one. The Cape Town router just discovered Johannesburg router automatically. So they exchanged hello packets on a serial WAN link, agreed on area 0, and then shared their LSDs and formed a full adjacent, not just a manual route configuration. So there is no IP route commands. OSPF did it automatically. All right, let's quickly go to Durban. Where are you, Durban? There is Durban. Okay, configure terminal. And then router OSPF 1. And then so there's going to be a router ID 3.3.3.3, and then network 10. 10.5.0 and then 0.0.0.255 and then area 0. And then the WAN link to Johannesburg, so it's network 10.10.101.0 0.0.0.3 and then area 0 and then end. Again, we can just watch it a little bit and then we should see the message. There we go. So you can actually see there. Now we can actually verify OSPF. So there's four key commands, commands that we can use. So here we can just say show IP OSPF neighbor. Then we can see the 1.1.1. So here's so if we do the same thing on Johannesburg, if we say so in Johannesburg we should see two neighbors, right? Show IP OSPF neighbor. Just trying to get neighbor, the correct spelling, and then we can actually see two of them. So here's the most important OSPF verification command. Let me teach you how to read it. Neighbor ID, that's the router ID of the neighbor, like 2.2.2.2 for Cape Town and then 3.3.3 Durban, for Durban on Johannesburg, and then PRI, so that's a priority. It's used for DR or BDR election. So one, which is default on serial link, so it's not relevant here. And then the state is the current OSPF adjacent state. So if it says full, that means that anything else, it should actually be full. If you don't see full there, anything else just means there's an issue or there's a problem. And then we've got a dead time. So the dead time is a countdown timer, which resets when the hello is received. So it should be around 30 to 40 seconds counting down. Right, you can see mine is between 36 to 39 seconds. And then the address basically is the neighbor's interface IP on the shared link. So it's 10.10.102 for Cape Town serial, and then 10.10.101 for .2 for Durban serial. And the interface, which local interface faces the neighbor. So you can actually see serial 2 and then serial 0, 0/2.1/1, and then the last one, the other one is serial 0/2/0. So the state column is what matters most, because full means that these two routers have fully synchronized their link state databases and are actively just sharing route information. If you see init or two-way or extart instead of full, so the adjacent has not formed completely and the routes will not be shared. All right, so we can also show IP route Just want to make sure that I can. So you look at the routing table. So the O, you see the O's. Let me just try and highlight it. There is the O's here. So the O entries, O is for OSPF, right? So it is automatically lent 10.10.4.0 via 10.10.100.4, sorry, .2, which is Cape Town, and then 10.10.5.0/24 via 10.10.101.2 for Durban. So the 110/65 just means administrative distance of 110 and cost 65. So the serial link cost of 64 plus the connected link cost of 1. So OSPF just calculated this automatically using the OSPF algorithm. So you can compare it with the previous lesson as well. I want you guys to go and rewatch that video again. So we've placed all of that we actually replaced all of that with 5 OSPF network statements per router, and the results is actually better because these routes now they now adapt when the link fails. So the next command that you can actually run is show IP OSPF. Now this command shows OSPF process details. So the router ID 1.1.1 confirming that our manual setting took effect, and then process ID 1, the SPF schedule, how often the router recalculates the path, and then the number of times the SPF has run. So this increments every time the topology changes. So in a stable network, this number grows slowly, So in a flapping network with links going up and down, it grows rapidly. So again, that's a sign of instability. All right. So now, and then the command number 4 is to show IP OSPF database. So you can see all the router LSA entries for all 3 routers. So this is the link state database. So the complete map of OSPF area. So every router LSA represents one router's view of its own link. So you can see LSA from all the 3 routers, 1.1.1 Johannesburg, and then 2.2.2.2 Cape Town, 3.3.3.3 Durban. All routers have identical copies of this database. So, and that is a beauty of a link state routing. Every router has the same complete map and just makes it its own independent routing decision based on that map. So we can go back and test again. And so I'm gonna go to Finance PC, and then I'm gonna just test ping Cape Town somewhere. Then I'm gonna just ping 10.10.4.10, which is some computer in Cape Town, and then let's see. So it should be working. The first one is always lost, but I never worry. But we see we're getting a reply there. All right. So this just testing end-to-end OSPF action. So let's ping Durban, a PC in Durban. So we're gonna ping 10.10.5.10, which is a computer in Durban. See if we can reach it. So there we go. So every single ping works. Same results as the previous lesson with static routes, but OSPF just achieved it with 0 manual route configuration. So there is no IP route commands, no next hop addresses to remember. Just 5 network statements.